Hello and welcome to lecture 63 of the course Computational Complexity. In fact, this is the last lecture of the course and there will not be any technical content. We will just summarize what we have seen over the course and I will share some concluding remarks which I wanted to share. So, I just want to summarize what we have seen. So, overall, what was the goal and how have we gone about trying to get closer to that goal, right? So, the goal was to understand computation, right? So, how much can we compute or decide, right? Compute in the sense of a function and decide in the sense of a language if we had X amount of a resource Y, right? So, where we considered several resources. So, when I said resource at the beginning, maybe the only resources that we would have been familiar would have been space and time, right, in terms of computational resources. But then during the course we saw other resources like randomness was a resource, right, that we could use during the computation. Interaction, towards the end of the course we saw interaction being used as a resource, right, when you have the power of interaction. That could be a resource. In the circuit model, the number of gates, the depth of the circuit, right, and the fan-in of the circuit, these were resources, right. So these are the resources that we saw, we used we try to understand the computation, right. So on the basis of these resources, we classified computational problems into complexity classes, right. So if there is a language that can be decided in polynomial time, then it is called this language belongs to the class P, right. If a language that can be decided using polynomial space, or it is P space, right. So and so on, polynomial time, but then randomized computation, two-sided error, it was BPP, right, and so on. Interaction, we saw IP, AM, and so on, right. So these are the resources that we saw, right, and we try to understand many of these complexity classes and try to gain some understanding of it. So let me just try to list down what all we have seen during the course, right. So on the topics covered, we started with time complexity, right, where we saw things like NP-Completeness. We started with NP-Completeness, Cook-Levin theorem, polynomial hierarchy. Then we saw space complexity, right. There we saw complexity classes like L, NL, P space completeness, and so on, right. We saw results such as Savage's theorem, right. Savage's theorem, then the result of NL equal to co-NL, which was Immermann-Serapchiani theorem, right. This is what we saw in, I think roughly this is the highlights of what we saw in the space completeness, right. Then we saw Oracle Turing machines, right, very briefly, even though just for one or two lectures. We saw what are Oracle Turing machines. We saw polynomial hierarchy using oracles, right. In fact, I can also list that in time complexity section. I think I already listed that. Then we saw Baker-Gill-Solovay theorem, which used oracles to show that P versus NP cannot be settled using diagonalization, right. It cannot be solved using diagonalization. So even though the proof used oracles, the result has nothing to do with oracles, right. Then we saw randomized computation, right, one-sided error, two-sided error, and so on. So RP, ORP, BPP, ZPP, right. We saw how to boost the probability of success or reduce the probability of error. We saw that BPP is contained in sigma 2 and pi 2, right. We saw that BPP is contained in P by poly, okay. So this is what we saw in randomized computation. Then we saw circuits, right, which was another fundamental model of computation, where we saw classes like P by poly, AC, NC, right, and we saw the model that where Turing machines taking advice, and we saw that that was equivalent to the circuit model, like, right. We saw results such as Carr-Clifton theorem, which said that if SAT has polynomial size circuits, then the polynomial hierarchy collapses. Then we saw parity is not in AC0, right, which was like one concrete lower bound that we have in circuits. Then we saw the power of counting. Right? If we could count, what could we do? Right? So till now we had seen decision problems. So if you could count the number of accepting paths, what could you do? We saw mainly two things. One was we saw Sharpe completeness. We defined the class Sharpe completeness, and the fact that permanent is Sharpe complete, right? Permanent is Sharpe complete, right? And then we saw that we saw Toda's theorem, right, which was a very surprising or very interesting result, that the entire polynomial hierarchy is contained in P with a Sharpe oracle. So this indicates how powerful is counting. So if you could do Sharpe, then you have the entire polynomial hierarchy at your disposal, right? Then we saw communication complexity. Right? We saw the basic model and lower some simple techniques. Basic model, some simple techniques. We saw the Karchmer-Wigderson relation and connection to circuit depth. We saw the monotone depth lower bound for matching, right? And finally, we saw interactive proofs, like what could be shown if we could interact with the prover instead of just taking a static proof and verifying it yourself, right? So what is interactive proofs? That was interactive proofs. So there we saw the model IP, which was interactive proofs. AM, where the interactive proofs where the randomness has to be made public, right? Then we saw that public coins and private coins are kind of equivalent. If you have a private coin protocol, you could convert it into a public coin protocol, right? Then we saw that SharpSat is an IP, and we also mentioned and I also gave the outline of IP equal to P space, even though we didn't really see the proof in full detail, but most of the details were similar to the SharpSat is contained in IP proof, right? So these are the kind of high level idea of what all we did. Of course, all of this, many of these results were involved like half a lecture to one lecture, to some of them actually span 2 lectures, right? And many subtopics I may not have mentioned, but this is like the high level topics. So this is kind of a decent amount of content for this course. But yet the area is very vast and very interesting, and if you look up any computational complexity course offered in any university, be it in India or be it in abroad, outside India, you will see that almost everyone covers time complexity, space complexity. Okay, so I said space complexity, right? Randomized complexity classes, circuits. Some of these are kind of standard in any complexity theory course, maybe 70% of it. But then maybe towards the end, maybe communication complexity, perhaps not everybody would do. Maybe some of them may skip the power of counting. So there may be some 30% may be left to the to what the instructor likes, or maybe the personal preferences of the instructor. So it's nice to actually go through different course pages of various offerings at various places of the same computational complexity course, and you see that everything, there are some things that are standard, some things that changes from place to place and instructor to instructor, and sometimes even the same instructor may change some topics, right? Because some advanced topics, because the area is very vast. So if you look at Aurora Barak, there are so many topics that we could not cover, right? So I was just about to come to that. What are the topics that we could not cover? So I'll just list. So there are too many topics that we did not cover, right? So I cannot list everything, but maybe I'll list some of them, right? So one of them is the area of zero knowledge proofs. Okay, zero knowledge proofs. So this is also a kind of an interactive proof system where there is a prover, verifier, etc. But there the prover's goal is to convey that something is in the language, right, to the verifier, without having the verifier learn anything about it, right. So this is why the prover convinces the verifier, right, but he does not give any other information except that the statement is true, right. So this seems like a very strange thing to say, because if I want to convince you that some statement is true, but I don't want to give you any more information, how is it possible, right? Because the statement that X is true will usually have a proof. But then I want to convince you that statement is true, but then I do not want to give you any more information. So how do I prove it without giving any more proof? So this is a small area, is an area of zero knowledge proof, which is very interesting, right? Another area that we did not devote any time to is cryptography, right? Hard functions, let's say, right, or maybe one-way functions. Sometimes people call it one-way functions. So basically, cryptography is to securely encrypt messages, right? So how do you encrypt messages so that the other party or no intruder can detect, see what is happening, or even if they get hold of the message, they will not. It should not make any sense for them. Right? It should be difficult for them to decode. So there is this notion of one-way functions. So meaning it is easy to encrypt, but then it is not easy to decrypt. Right? So it is so. It's like a one-way road where it's easy. You can go on one way, but cannot come back that way, the opposite way, right? So one direction of computation should be easy, but the inversion should be hard. So again, this is an interesting area of complexity theory, and you may see some other course offering covering some of these topics, right? Another interesting area that we did not cover is PCPs and hardness of approximation. Okay. Sorry. Right. So there is a one way to tackle NP completeness, or to one way to deal with NP completeness is to so if some problem is NP complete, what is the next best thing that you can do if you only have polynomial time to deal with it, right? So one thing that you can do is what is so called approximation algorithm. So you cannot get the optimum solution, but you can get, let's say, twice the optimum, right? So for instance, if you are trying to find the smallest set that has a certain property, so let's say the smallest set has size 10, for instance the vertex cover has size 10, but you assure that you will produce a vertex cover, but that is not too large. So you will say that I will give you something at most twice the size of the smallest vertex cover, so approximately optimal. So this is what is called approximate algorithms and approximation algorithms, and PCPs are what is called probabilistically checkable proofs. So it's an offshoot of interactive proofs we saw in the last week, in week 12. And PCPs interestingly gave rise to the theory, a lot of improvement in the area of the hardness of approximation. So people were able to make statements such as this. You cannot even approximate this language within this factor unless P not equal to NP, and so on. Right? So that was an interesting area, and that is also very interesting. In fact, at some places there have been entire courses on PCPs and hardness of approximation, and and same is true for even cryptography. There are courses. Another interesting topic that is pseudo randomness. So there are and maybe de-randomization. There are somewhat related topics. So pseudo random objects are something that look like random but are not completely random. And so there are like graphs or other objects, sets or sequences which are pseudo random, and sometimes it's interesting to understand how they are generated or how you can get pseudo random objects, because sometimes it's helpful for de-randomization. So what is de-randomization? So we saw randomized algorithms or randomized complexity classes, and I mentioned at the beginning of just this very lecture that randomness is a resource. So can we because it's a resource, we do not want to we want to try to minimize how much randomness we use. So can we reduce the randomness of a certain that is used by a certain algorithm? So that is the idea behind de-randomization, to reduce the randomness or sometimes maybe even remove the randomness entirely. So if you can always remove randomness from a randomized algorithm, that would mean that, so it is like trying to understand randomness. So we know that BPP contains P, but is BPP strictly more powerful than P? We do not know, right? Is there something that can be solved only using randomness but cannot be solved using deterministic polynomial time? We do not know. But if any algorithm you can remove the randomness without blowing up the time, that means randomness is not really a useful resource, right? So this is one other interesting topic. A couple of more interesting topics. So one is quantum computation, quantum computing. So quantum, in the quantum world, bits are not stored as 0 or 1, they are stored as superposition of 0 and 1. And then when you make a measurement, then it becomes 0 or 1 with some probabilities, right? And then using that you are able to do some computations, and you need specialized you need slightly different techniques to understand the powers of quantum computation. So for instance, factorization can be efficiently solved in the quantum setting, right? So quantum computation is an interesting topic in itself. I am just talking about the computation part of it, not the physics aspect of it, which is also an extremely interesting field in the physics aspect. And one more point that I want to mention is Boolean function analysis. So this is not really a sub area of complexity theory, but it's a related area. So you can look at Boolean functions, as in functions that are of the form f01 power n to 01. So the function is 01. Right. In this case, so this is a Boolean function. So now we'll try to understand this a certain function or a class of functions by studying it. So one of the popular tools is the Fourier analysis. So given a Boolean function, there is a way to look at it from another domain by doing a Fourier analysis. It's not the same Fourier analysis that is used in signal processing, but it's similar, but it's slightly different. And this actually has a lot of applications in complexity theory, as well as other areas like sometimes combinatorics as well. So this is another interesting associated area, and many other and many more. Right, this is not the only set of topics. Many more topics are there that are interesting. But then of course we only had 12 weeks, and I had to pick some topics that needed to be covered, and hence I went with whatever we have in the course. But then there are so many other interesting topics that we could think of that we could have thought of including, or if you're interested, I would certainly say look up each one of them and try to read about it or learn about it, right? And in fact, each of these statements that we said, each of these bullet points that we actually covered, and even within these bullet points, there are much more things to be explored, right? So you could try to read up or understand it yourself. Again, this is a introductory graduate level course, introduction to the area, right? So, or maybe an invitation to computation complexity. So if you're interested, then there is a lot more that you can learn and understand. I hope many people are excited by this area, and many of you go on to learn and do much more in this area. This course is just the starting, right? And finally, some more points, some general comments. Right. So one is that this is the first time I'm delivering a MOOC, or the first time I'm also teaching on over the NPTEL platform. So there could have been issues with my with the way I delivered stuff, or with the way I chose stuff, right? So so there could have been many things that could have been done better. So but then the challenge is that and I do not have real time feedback while teaching, right? But I know that many of the students may be learning from different backgrounds, so I have tried my best to explain the content to as detailed as I could possibly. But at the same time, I also wanted to do justice to the course material. It's a graduate level course, or which is a postgraduate or PhD level course in computational complexity. So I also wanted to do justice to the course contents. So I had to balance between these two. So my first MOOC, right, over, and first one over NPTEL, and in fact I think we covered a decent amount of material, right? We covered a decent amount of material in this course, not very much, but it's a decent amount that we have covered. And so if you have I'll be happy to hear any feedback from any of you. I know the NPTEL has a mechanism to collect feedback, but then I also welcome you to write to me directly, right? So please write to me at so my email ID is subruk@iith.ac.in. If you Google it, it should not be too hard to find. subruk@iith.ac.in, and feel free to let me know what contents you liked, what could have been done better, and are there some content that is some topics that are completely hopeless that you would like me to redo. I can of course check with NPTEL, and if there is a provision to replace some of the video lectures, if there is sufficient, if people feel that it should be replaced with a different presentation. And another question that I have to think of when I'm deciding what to teach, and even if I decide I'll teach this theorem, right? So this so there could be a specific theorem, let's say permanent is sharply complete. There are, if you look at textbooks, and if you look at different lecture notes at different places, there are multiple ways. Some, even though the proof is essentially, sometimes the proof is essentially only one, but then there are multiple ways the same proof can be presented. And so I have to make a choice of which of these presentations is the best, right, to be for this particular mode of interaction. So, so there are so many choices that one has to make while teaching. So the point is, if you have any feedback or comments, I always welcome feedback and comments, and feel free to be honest and candid with me on that. And anything about the speed of the course, about the pace of the course. Is it too fast, too slow, right? Because this is like a static delivery without feedback, right? It's not like we are interacting, right? So we just saw interactive proofs. So of course we have interactive live sessions, but then that is not, it's not like after every lecture we have one interactive session. Like we had like 5-6 interactive sessions throughout the 12 weeks. And even again, if you are a viewer who's just happened to watch the lectures on YouTube or the NPTEL platform, but not really registered and learning, and you happen to reach the last lecture of the course, and you're hearing me say this, you're also welcome to write comments to me. And yeah, I think that's about it. Please feel free to write feedback. So any feedback is welcome. Any feedback is more than welcome. Yeah, and I hope you had fun learning the course. That's all from me. Yeah, thank you.